Can you please confirm if I am audible and you can see my screen? Maybe you can write in the chat box. I hope I am audible to you. Let's wait for a couple of minutes so that people can join. I will start after that. think we can start. So let's start the session. Let me introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. So welcome to the live session for the course Sensor Technologies, Physics, Fabrication and Circuit. This is week 6. So the purpose of this live session is to give a brief summary of what we have discussed, what was taught in this week, as well as to solve few problems. Those will be helpful in solving your assignment for this week. I will be in the presentation mode for the session for the most of the parts. So if you have any question in between, you can write in the chat box. I will check the chat box in between, and I will try to answer your question. If I cannot answer, I cannot give you some answer to some of your question, then I will note it down, and we can have it in the last session, or probably we will have a doubt clearing session before the exam. Now I have not gotten any response whether I'm audible or not. I hope I am audible, and if you face any like disturbance, or is there anything you cannot hear me properly, or cannot see my screen properly, then let me know. Okay. And I'm also recording the session just for your information. Please don't hesitate to unmute yourself in between if you have any doubt or if you want to answer. Okay. So let's start the session. First, I will give a brief summary of the topics those were covered in this week. The main purpose of these live sessions are for solving problems and to clear your doubts, but since I always start my session with a brief summary, because that will be helpful in solving those problems. And anyway, in this week we don't have many numerical questions. Mostly we have like these theoretical concepts of microfabrication techniques. We will have some questions related to them. Okay, there are people who have joined. I hope there are people. So what we studied this week, different microfabrication techniques. So microfabrication techniques involves these processes. So if you want to make a device, a sensor or something, like if you want to make a device or sensor, you have to use these microfabrication techniques, and that involves these processes. There are few processes those are involved. So first is deposition technique. So deposition means deposition of a material on a substrate, right? Now, to deposit a material on a substrate, there are various techniques, like I will discuss later also. Physical vapor deposition and chemical vapor deposition and other techniques. Basically, the deposition techniques can be classified into two categories, either physical techniques or in a chemical technique. So in those techniques, especially in chemical deposition techniques, the material that you are going to deposit and the substrate that you are using, that has to be specific. Like you cannot deposit, or you cannot grow certain like material on certain substrate, I mean maybe you can grow, but the quality of the film or of the material will not be that great. So a certain chemistry is involved. That is mainly like very significant in case of chemical vapor deposition or in any chemical methods. It is somewhat dependent like important in physical techniques also. For example, the substrate you are using and the material that you are depositing, the adhesion between the material and the substrate may not be that great, so your film may be peel off. Like suppose you have the substrate and you have deposited a thin layer, you may observe that with over time or due to some other condition, environmental condition, the film may peel off. Something like this may happen. So that is why using this using a certain type of depending on the material, you have to select the substrate, and then there are different substrate also. Most of those are rigid. Suppose you want to make a flexible sensor, then in that case you have to use a flexible substrate. Now many of these deposition techniques may be high temperature processes, so if you are using a flexible substrate, then you have to be careful that suppose the deposition techniques require a 200 degrees Celsius, mainly it is generally more. So suppose it is a high temperature process, then you cannot use a flexible substrate, for example. So deposition is uniform deposition, basically uniform deposition on film. You can use certain type of shadow mask also to make a patterning, but I'm also including that in deposition part. Say this is your substrate, this is the top view, and say you have covered this with some material, maybe some tape. We use in our lab Kapton tapes, say this is a Kapton tape maybe, and then you deposit the material that you want to deposit, and then you remove this Kapton tape. After that, maybe you will get your film here. This will be your substrate, there will be no deposition here. Then again this is your film, and this is a film. So you have two portions where this is substrate and this is a film. So in this way also you can make a pattern, but you have certain limitations, because if you want, this process is called shadow masking, so you are masking some portion of the substrate. Using that technique, there is a limitation that you cannot say cut these strips very thin. So this technique is useful only at like very specific cases. But if we want to pattern, say we want is like this is our substrate and we want our deposition, this is the side view, okay, and this is top view. So if we want our deposition to be like this is our film or the material, and this is the substrate. To make this kind of pattern, one fabrication technique, one process of fabrication technique is called patterning, and there are various patterning techniques. In this week we studied about photolithography. I will discuss more about it later, and there are other techniques of patterning also, right? Next technique is etching. So what etching means? Etching means select, basically it is removal of material. Say you have a uniform film on a substrate, This is your substrate, and you want this kind of pattern. So etching means you want to remove it at certain portions, so that you finally get a structure like this. So you have removed these portions from your total structure. So this process is called etching. Now you may think like this and this patterning is same, but often to do etching we need a patterning technique, and then we do the etching, which basically gives us selective removal of material from a substrate or like from underlying layer. There may be another film below it also, but you want to specifically remove the top film, certain portion of the top film. So this process is etching. Next, doping. So doping is a process that is associated with semiconductors. Now why we do doping? In case of silicon, we do doping, say we make it p-type or n-type. If we dope silicon with boron, then it will be a p-type semiconductor, and if we dope silicon with arsenic, that will give us a n-type material. So why we need p and n-type? So that we can have like different conductivity, we can control the doping concentration, and that's how we can get different properties of the material, different conductivity, different mobility. And you know that because of doping we can make like devices like p-n junction, which is like a very basic device. You will find p-n junction in other devices also. For example, in NPN transistors also there are two p-n junctions, right? So doping is necessary for that. So it is a process you may or may not use in making a sensor, but other three techniques we typically use. For example, say you have a substrate and you want to deposit with some material. So for that, this will be your sensing material. For that you will be using some deposition technique. Then after that, say you want to deposit 2 electrodes so that you can measure the resistance of this sensing material, right? So to make these electrodes you will be using patterning and etching. So these are electrodes. So you can see that to make a basic sensor, basic resistive type of sensor with a uniform sensing element or sensing film, you need these macro fabrication techniques. Now micro, that means you are dealing with characteristics length in micron. In many cases it may not be like in the micrometer regime. Say for example, the size of these electrodes you may not require in micrometer dimension. It may be larger than that, but the processes are kind of same. So different techniques are classified, those are involved, associated with fabrication of any sensor or any device in that case. Now typically these processes are done inside a clean room. So what is a clean room? That was discussed in the lecture series, so I will not go through it, different standard or different types of clean rooms. This is a picture of a clean room I have taken from internet. You can see here the ambient light is yellow. So why they use yellow color light in clean room? Mainly where the patterning is done, where the photolithography processes are done. So the photolithography process involves using a chemical which are known as photoresist. There can be different types of photoresist, but these photoresist in general are sensitive to light. Now the typically what light is used, UV light source is used. So the photo resist, the chemical composition is such that the photoresist are sensitive to UV light or blue light. So uh, in the ambient environment or the lighting that is used inside a clean room is yellow, so that it does not interact with photoresist, or the light does not change the properties of photoresist. Okay. I hope the things are clear and there are no questions. So next I will discuss different deposition techniques. So deposition techniques can be classified into these three categories. First one is physical vapor deposition, second is chemical vapor deposition, and thermal oxidation. Thermal oxidation is not a typical deposition technique. It is basically growth of material. This is growth. Whereas in these two techniques, we actually deposit a material on a substrate using some source. Now, physical vapor deposition, as the name suggests, it involves physical processes, right? So what are different PVD techniques? First one is thermal evaporation. So what happens in thermal evaporation? The basic technique is that there will be a boat or a crucible or a basket, depending on the system. Here you will have a material. This material you want to deposit on a substrate. Your substrate will be kept here. This is the typical configuration. This will be your substrate. This is the boat where you will keep your material. Now the material you want to deposit should have a lower melting point compared to the material using which the boat is made. Now there are different techniques to create a physical vapor of this material. The basic one is thermal evaporation, where you will apply a current to this board, and this board will heat up due to Joule heating, and because of Joule heating, this will melt the material you have put here. Now in physical vapor deposition, mainly these techniques are done inside a vacuum chamber. So the material, the vapors will, so the atoms will be like, it will ejected, the vapors will like evaporate, and because it is done inside a vacuum chamber, these atoms will not, so if it is done like in a low pressure in a high pressure condition, if it is in a low vacuum condition, then there will be other material also inside the chamber. Now these vapor like these elements, these atoms might have collide with the other particles, those are present inside the chamber, but we create a vacuum inside these evaporation chambers, so that these materials will directly go in this direction and sit here at the substrate. So that's how we get a uniform film. Like over time this will be a uniform film, and we get a uniform deposition of the material on top of the substrate. Now this can be a thermal evaporation techniques, it can be an e-beam evaporation techniques, where you use electron beam to evaporate these material. your target material. But irrespective of the technique, this is done. This has a configuration like this. Like if you ever looked at a thermal evaporator or air beam evaporator, this is kind of like a configuration you will get. This is the hardware, a similar hardware you will see. Now sputtering is a bit different compared to thermal evaporation and e-beam evaporation. What happens here in case of sputtering is that we create a plasma between our target and our substrate. So this is our substrate, and this is the target. Now I introduce a gas between these, typically argon. Now what will happen, this argon will become argon plus an electron, and we apply negative bias to the target. So argon plus ion will come here and it will hit the target and will eject some material, eject some atom from the target, and those atoms will sit at the substrate. Okay. This is the basic of sputtering technique. There are different types of sputtering technique like DC sputtering, RF sputtering, but the basic working mechanism is like this. We create a plasma using a gas. Typically we use argon gas, and argon gas will hit the target, it will eject some atoms from the target, and the atoms will sit at the substrate. Okay, so this is a sputtering system. We have a this sputtering system is from HSV in the IVAC. So we have a similar system in our lab. So here you can see this is a load lock chamber. So we don't open this main chamber here. This is the main chamber where the deposition happened. And this is the controller part. This is the controller. So we don't open this main chamber directly. We place our substrate here, and it is internally transferred using this controller setup. This is transferred here. So this is the substrate holder, if you can see. Here we place the substrate like this. As I mentioned here, the substrate is kept here. So we keep our substrates here, and this is the target. In this system there are 3 targets. Like this is one target, this is the second, and this is the third one. Okay, there are 3 targets. At a time we only activate one. That means we create plasma near only one target, and we can do like multiple deposition, like layer by layer, up to 3 layer using this system. So there is a gas valve near, like a pipe, something like this, near this target, and we apply we put argon gas here, and that will create plasma between this substrate holder, the substrate and the target, and the substrate atoms, and target atoms basically gets ejected and sit at the substrate. So this is one system we have in our lab, and I have used this system also. So the idea is that in all of these PVD techniques we have this kind of setup. Like we have a main chamber. We may or may not have a load lock system, but in most cases we have. And this chamber we first create vacuum so that we don't get any unwanted deposition, and then we do the deposition. Either like the controller there can be manual like valves and knobs, and this is mainly an automated system. So where you press commands here, give commands from here. This is the control like command window where from you give command, and the processes happen. The deposition happens inside the chamber. in vacuum. So if you remember, we introduce argon gas. So before putting argon, we create vacuum, and once we put argon, the pressure is still low, but so that we can get deposition, but it's not in very high vacuum at that point of time during deposition. So this is about physical vapor deposition. Next is chemical vapor deposition. Now I'll talk about it, chemical vapor deposition, later. So in the next slide, there are different types of chemical vapor deposition based on the pressure at which it is done. So as the name suggests, atmospheric pressure CVD, here the CVD, the chemical vapor deposition process, is done at atmospheric pressure. This is relatively simple because you don't need any vacuum system to create any system to create vacuum. Next one is the low pressure CVD. Here you need a pump to create vacuum, but the advantage of this is that you get very uniform layer. Maybe there will be less contamination, you will get better quality film. But the disadvantage is that compared to atmospheric pressure CVD, it will be expensive. Next is plasma enhanced CVD. So as the name suggests, CVD processes involve some chemical reactions to happen between the substrate and the material that you want to deposit. Those chemical reactions are typically like high temperature processes. Now using plasma enhanced CVD process, you can using plasma you can do the deposition at a much lower temperature. That will maybe helpful in certain cases, because maybe sometimes your substrate or the overall it will be more energy efficient, I would say, and you can do the process at much lower temperature. Okay. Now in CVD there are different steps that happen. I have given you this list. What happens first, so in a CVD chamber you will have a tube. So this is generally quartz tube. The one we have in our lab has a quartz tube, because it can handle high temperature. And say you keep your substrate here. Now you introduce the reactant gases. From one side there will be a controller here, so that you will pass a very controlled amount of gas through to this tube, and you often mix that with some carrier gas that will not interact with your material or with substrate. This is just a carrier gas, and the pressure of this carrier gas will be higher, so that it can actually push the reactant gas towards the substrate. Okay, so the reactants will come here in vapor form. Now the reactant molecules will be adsorbed. You know what is adsorption? It is not absorption. It will sit at the top layer of the substrate, and that may decompose into other intermediate states of the reactants, which is the third process, chemical decomposition, reaction and surface migration. Once the reactant gas reaches the substrate, reaction will happen, chemical reaction will happen between reactants and substrates, and it will form a uniform layer of the reactant gases, like whatever the material that we want to deposit. And after that, desorption of the byproduct from the substrate. Say due to these chemical reactions, some byproducts may be oxygen or some other byproducts, those may result from the chemical reaction. Those byproducts will dissolve from the substrate, and these byproducts will be taken away by the carrier gas outside from the tube. So this is basically CVD process. Now what pressure you maintain between inside this quartz tube or the tube that you are using, or what is the mechanism that you are using, like to provide energy, sufficient energy to make this chemical reaction happen. Depending on that, you can categorize chemical vapor deposition techniques into different categories. I will not go through it, but you should look into the advantages and disadvantages of different types of CVD processes. Okay. Is there any question? I want to know, like I always give a summary before starting the session. Do you think it is useful, or I should directly go to the problem solving session?
It is useful.
I think these few slides you can look back later also. If you don't have time to go through all of your notes, then maybe you can go through these summary notes. Next topic is patterning. So we have discussed about deposition techniques. Next is the patterning techniques. The one that was discussed in this week was photolithography. So I had taken this image from Google. It shows different steps of photolithography. So what we do in photolithography basically, so this is for silicon substrate and there is SiO2 layer. You can just think about it, some layer, it may be substrate or substrate plus some film, and you want to make a pattern on top of it using some material. You want a final result, something like this. Okay. So what you do, first we put a photoresist layer on top of it. What is a photoresist? Photoresist are basically polymer material. Those are photosensitive. There are two types of photoresist, positive photoresist and negative photoresist. In case of positive photoresist, when you expose it using light, what we use UV light, or even it is sensitive to blue light also, like it depends. Like you can check the data sheet of a positive or negative photoresist. You will see for which wavelength these photoresist or these chemicals are sensitive. So in case of positive photoresist, when it is exposed to light, it becomes okay, in case of positive photoresist, let me think once. Okay, so it becomes so we are using positive photoresist. Okay, in case of positive photoresist, it becomes soft. You can see this is a mask, and light is coming through these slit areas. Okay, so in this portion, light is incident on the photoresist, and after these processes, what you do, after this you develop. What is development? You basically dip it in a developer solution that is specific to the photoresist, and since this becomes soft in case of positive photoresist, it will become soluble inside the developer solution. So what we do, like we do the exposure, and say this is a beaker, we put the developer solution here. This is developer solution. and we dip the sample here. Now we maintain certain timing so that we get like good development, and when we take it out we will see the patterns. Okay. Obviously in case of photolithography this will not be very visible using naked eye, so you have to use a microscope because these are generally in micron sizes. What happens in case of positive photoresist, the portion where the light is incident, that becomes soft, so that's why this portion of the photoresist gets removed, and in case of negative photoresist it became hard and the other portion becomes soluble in the developer solution. Okay, after this step, so this is basically the lithography is done. So next here the transfer technique is used. Here like you can see that the deposition of the material is done. I don't know why they are using this. Okay, please don't look at this portion of the, I don't know what they did. So let me explain, like I will explain. So this after the development in case of positive photoresist, after this step you got these pattern. Okay, so this is pattern photoresist. Now what you can do in the next step, say you want to deposit some material, say some metal, so you deposit some metal on top of it using some physical vapor deposition technique, right? So what it will result, so this is say some metal, there will be deposition here also. You know the difference between PVD and CVD. So in case of PVD we get this kind of deposition, this kind of profile, so you get, this is metal deposition, metal or any material. Now what you do, what we normally do, we do a process called lift off. We remove these photoresist using again some chemical. So I have used acetone in our lab. It can be some chemical that will actually remove these photoresist layer. Okay, so when photoresist will be removed, the top metal layer will also be removed. So final pattern what you will get, this is your substrate, this is the material you have deposited, and this is the material that you have deposited. Say you have deposited gold on top of this photoresist, so you will get strips of gold on top of your substrate. Okay, so this is photolithography. Till this process it is photolithography, and this is deposition, and then like you get the final pattern. Okay, you can use different etching process also. Okay, but this is the lift off process is a very basic process using which you can deposit some material using photolithography and a photoresist. Now what will be your final pattern? So if you use a positive photoresist, this will be your final pattern after metal deposition. Now if you use a negative photoresist, your pattern will be opposite. If your mask is same, then it will be something like this, right? So you can see based on your requirement what is your final design. You can either use positive photoresist or negative photoresist, and you can use the same mask. Okay. So this is about photolithography. I hope things are clear. Give me let me take a break for a minute or so. I'll go to the problems next. I hope there is no question. So let me write down the first question. The photo mask should be in contact with the substrate during photolithography because. So what is the reason? The options are: A, UV light does not travel in straight line; option B is the UV light would incident on the unwanted reason if the photo mask is not in contact with the substrate. Option C is the photo mask holds the substrate in place. Last option is none of the above. Try to give me the answer in the chat box. I am waiting for a few minutes so that you can answer. The photo mask should be in contact with the substrate during photolithography because. What is the reason? any more answer? So the answer is, the first option is UV light does not travel in straight line, which is not true. UV light travels just like other light or other wavelength in electromagnetic spectrum travels. Correct option is option B. The UV light would incident on unwanted reason if the photomask is not in contact with the substrate. So if this is your substrate and photoresist is on top of it, if this is not okay, so my diagram is really bad. So this is your substrate, and if this is the mask, and if this is not in contact, so light will look like this. So you want a pattern which has a size X, say, but you end up getting a size, because of the exposure, some Y. Okay, so suppose you want a 10 micron size and you end up getting a 12 micron size. So your contact should be proper between the photomask and the substrate or the photoresist. If you don't know what a photomask is, so it is generally a glass substrate, and there are patterns made using chromium. Okay, based on your design, some portion of these will be covered using chromium. So this portion will be black and this portion will be black, and rest of it will be glass. So light will pass through it, and the portion where chromium is present, so it will be light will not pass through it. So that is a photomask. Third option is photomask holds the substrate in place. So basically, in case of a photolithography system, so the mask will be on top of it. So there will be a mask holder, and you place the mask here. This is the mask, and using a vacuum, there is a vacuum groove, and if you using some pump, a vacuum will be created between this mask holder and this mask. Okay, so the mask will be in place, and you place the mask like upside down in your system. So there will be your mask, and there will be another stage. You can pull this out, and you can keep your sample here. Then what you do, there will be X, Y and Z movement now. So using that Z movement, you push this substrate upwards and make the contact. So I think this is how the most photolithography system is configured. Like the hardware setup is like this. So the one I use have this kind of setup. So there is like a vacuum chuck for this to hold the mask, and for the substrate we typically have a sticks. I'm not aware of like other type of lithography machines, like other configuration there may be, I'm not very sure. But the task of photoresist is not to hold the substrate in place, so this is not correct. So I want the people present in this meeting also, like other people also, like so that I get answer at least in the multiple choice questions, because most of the questions in the session will be theoretical, so you can just answer A, B, C, D or 1, 2, 3, 4. Try to answer that. Let's go to the next question. Let me write down the question first. So what are the steps or the sequence of steps in a lithography process? Washing in the developer solution. Putting the photo mask on top of the substrate. As I mentioned in the last question, like making proper contact between the photoresist and substrate is crucial. So this is one important step in the lithography process, and this is very important if you have multiple lithography process. Say suppose you have already a pattern something like this, and you want a pattern on top of it also like this, smaller strips. Okay, in this case putting the photo mask on the top of the substrate, making proper contact and proper alignment is very important. Like it's one of the crucial steps in a lithography process. Third is UV treatment. Metal deposition. Fifth is spin coating photoresist. metal etching, removing photoresist. So what is the sequence? The options are A, 2, 3, 5, 4, 5, 1, 6. What I did, so this is double. Option B is 2, 3, 1, 6, 5, 4. How it can be forgotten. Five, 2, 3, So these are the options. I have discussed about photolithography process. It was discussed in the lecture videos also. So give me the answer in the chat box. The sequence may not be same as the one that I have discussed in like just before starting the problems, because there I discussed metal deposition using lift-off technique. Here it may be different. You can go through the options carefully and think about it and tell me the answer. I'm expecting at least few answers for this. Even if you don't give me the total sequence, like the sequence for metal deposition and etching, at least you can give me the sequence for the lithography step. No answer. Read the question again. So you already know what is the lithography process, basic lithography process, and try to match it, or at least give me what is like the steps in lithography at least. Option is D. Okay. Any more answer? D is the correct answer. Let's see how it is correct. Okay. So I have given you the hint that this process is not a lift off process. Metal deposition is not done uh, by lift off here. So here, so you already know in case of lithography what will be the steps. So first you need a photoresist layer that you will spin coat. Okay, and after that spin coating, you will put the photo mask on top of the substrate. So the sequence, I don't know from what it will start. There will be the lithography part will have the sequence: spin coating of photoresist, and then putting the mask. After that, UV exposure. Right? You will do UV exposure. After that you will do development, washing it in the development solution. So this is one, and we don't know the rest of the processes, but these four are in sequence that you will do. And I think by looking at the options also, you can directly say, if you know this sequence, then the correct option is option D. I will explain the process here, the process that is given here. So in this process, you have a substrate. So this is basically patterning and etching together. You have the substrate. You do uniform metal deposition using some techniques, say some PVD technique by sputtering or thermal evaporation. So your step 1 is metal deposition. Now you don't want a uniform film of metal, you want some patterning. So what you will do next, you will spin coat a photoresist on top of the metal layer. My drawing is not very good, but I hope you are getting the point. So this is photoresist. How you will coat photoresist on top of it? By using a spin coater. So what a spin coater will do, you put few drops of photoresist. It's a chemical, it's in liquid form. Mostly it will be in liquid form, especially the one process that is given in the question. So the top view will be like this. You have the film, you will put few drops here, like I don't know how the drops will come. So we'll put some photoresist material here, and the spin coater will rotate this at very high speed. Okay, and after that you will get a uniform coating of this material. It will spin coat, like it will rotate the liquid material, the liquid photoresist, to get a uniform coating. Now based on the rotation speed, you will get a certain thickness of the photoresist. So the next step is spin coating of photoresist. Next step is will be you have to do the contact proper and alignments of the mask. Scissor metal, this is photoresist. Say this is your mask. So third step is making contact between photoresist and mask. Okay. Now we usually what we do with after spin coating, we do baking, pre-exposure baking. So what we do, this will be in liquid, like there will be uniform layer of liquid on top of the substrate. We put it inside an oven, say at 100 degrees Celsius for say 10 minutes or something. Like it depends on your system at what temperature you are doing the baking and what photoresist or what chemical that you are using. Why this step is necessary? So the photoresist, it like there will be that will be in some solvent, so it is in liquid form. So the baking process actually hardens the photoresist layer like little bit. So we typically do this, but in the option it is not given, so I have not mentioned here. But spin coating of photoresist, usually after that we do baking. Okay. Then we make the contact between the mask, photoresist and the mask. Next step we do UV exposure. UV exposure for certain duration. So our photoresist will be sensitive to certain wavelength, and we normally require a certain amount of light exposure to actually like harden or soften the photoresist. You will find that those in the data sheet of a photoresist, the unit is generally given as millijoule per centimeter square. So based on that, for certain duration we'll do the UV exposure, and after that we do development. Okay. So what we do in development, we put it inside a developer solution for that specific photoresist, and say this is a positive photoresist. So due to the exposure, this portion will become soft, and after the development we will get a pattern something like this. This is substrate, metal, photoresist will be like this. Now next step will be etching. Again there are different kinds of etching. Excuse me. There are different kinds of etching, wet etching and dry etching. Say you are using dry etching, you are putting some reactant gas or some like gas that will remove this metal. Okay, so etching will means the removal of this metal layer, or you are using some wet etching, so that chemical actually will etch out this portion of the metal, because this portion of the metal is exposed. So after etching, what he will get, will have a structure like this. We'll have metal here at this portion, we'll have metal here, and there will be photoresist. Okay, so the sixth step is etching. Okay, now you want the metal pattern, you don't want the photoresist on top of it, so you peel off the photoresist. Photoresist generally gets, like, you can very easily peel off, or you can use some chemical like acetone or something to peel off the photoresist layer, and finally you will get patterned metal like this. Say this is your 2 electrodes. You are making a sensor, you need 2 electrodes to measure resistance or capacitance or any configuration, like where you need 2 electrodes. Say this is a 2 metal layers, 2 electrodes. So last step will be removal of photoresist. I hope it is clear. I hope it is clear. Just give me a minute. You can tell me if you have any question. Go to the next question. E-beam lithography. So e-beam lithography was not discussed, I think, but it is similar to photolithography. So here, instead of a UV source, we use electron beam for patterning. Okay, basically it's very similar in steps wise, but it's different in certain aspects. Okay. E-beam lithography is preferred over photolithography for option A is batch process, B is a higher resolution of patterns, option C is mask is essential, option D is less parameter to optimize. So you can think about it and tell me the answer. What is the advantage of E-beam lithography compared to photolithography? And if you want, you can tell me what is the disadvantage of e-beam lithography compared to photolithography also. That is not in the question, but you can think about it and tell me. E-beam lithography is preferred over photolithography. For what reason? Because it is a batch process, or it gives high resolution. Whether it is whether we need a mask for the for e-beam lithography, or the last option is whether we have less number of parameters to optimize. Please go to the front slide. Which one? Front slide means the one that I have given for photolithography. The question 2. Okay. This slide or the question? So this is question 2. What are the steps in a lithography process? Remember, this is lithography plus etching process. Okay, the correct option is D. We do the metal deposition first, then we spin coat the photoresist, we place the mask on top of the substrate, do the exposure UV treatment, then we do development. That means we dissolve the photoresist, the soft photoresist part in a developer solution. Then we do metal etching. That will be like uniform, because there is a profile, like due to photolithography you will get a profile. So the etching will be like from, if it is a physical etching, it will etch out uniformly. That will like remove the top layer. And if it is a wet etching, that it will like selectively remove certain material, but ultimately we will get a patterned metal layer, and we at last we remove the photoresist, so that we get a patterned metal layer on top of our substrate. So that was the question. Is it clear? Okay, question 3, high resolution of patterns. Okay, that is the correct answer. In case of e-beam lithography, the advantage of e-beam lithography over photolithography is that in e-beam lithography we get higher resolution. Higher resolution means we can have like smaller feature sizes. Okay, so why it is like this? In case of photolithography, what source we use for exposure? We use UV source, right? That will have some like wavelength of this UV light will be in some hundreds of nanometers. So you know that visible length is in 400 to 700 nanometer. So UV is below this, so that will be like less than 400 nanometer, but it will be some hundreds of nanometer in that range. So depending on the type of the source, that wavelength will be different. In case of e-beam lithography, the source is electron beam, right? And electron have a wavelength as I hope you know about the de Broglie's theorem. So, as per the de Broglie's theorem, electrons have wavelength which is equal to h by m into v. Here h is Planck's constant. You know the value of Planck's constant, 6.62 into 10 to the power minus 34 joules second. M is the mass of electron and V is the velocity of electron. So electron will have certain wavelength, and this is the wavelength of UV. Now you cannot make a pattern using using a source, like you cannot make a smaller pattern compared to the dimension, like the wavelength of your source. For example, this is your this is the pen, like this is the tip of the pen. Now you cannot make a straight line, or you cannot make a line which is thinner than the tip of this pen, right? Similarly, you cannot make a pattern, a very small pattern, say 10 nanometer or 5 nanometer, using a UV source, because the wavelength is large. Patterning or lithography is just like writing, right? So you use E-beam lithography because the wavelength of electron is much less compared to the wavelength of UV source that we have in our traditional photolithography system. That is why it provides, E-beam lithography provides higher resolution, or we can make smaller dimensions of the patterns. Now the disadvantage of UV lithography compared to photolithography is that it is relatively expensive. And one more thing, in case of photolithography, you have a like concept of mask, right? I have shown you the mask here, right? This is a mask, and like we can expose it using UV source, like uniformly. We can have a large mask, and we can expose it on a large substrate in one go. Like we expose the light will be incident, and the whole substrate or the whole wafer will get patterned. But in case of E-beam lithography, what happens? It is a sequential process. What that means, if this is your substrate and it is coated with photoresist, in case of E-beam lithography, it will be like E-beam resist, which is similar to the photoresist, and then you will write sequentially. Okay, you will go like this. You'll go here and expose, and you'll go here, expose, and you'll do something like this. So this is a time consuming process. So this is one disadvantage of E-beam lithography, and overall the hardware or the instrumentation is much expensive compared to photolithography. Okay? That was the difference. Before going to the next question, let's go to the next question. Which of the following characterization is needed? To get the information about crystallinity of a material. Option A is Raman spectroscopy. B is XRD. C is UV visible spectroscopy. D is SEM. So what is the answer? XRD is X-ray diffraction, SEM is scanning electron microscopy. Again I will wait for some time so that you can answer. This was not discussed in the lecture series in details, but characterization of a material that was discussed briefly, and if you know the answer, give it answer, or I will give brief description of different characterization techniques. Those were mentioned in the options. Option B, yes. Here option B is correct. The correct option is to characterize a material and to know about its crystallinity. We use X-ray diffraction technique. Let me discuss about briefly about the other techniques also. I'll just give you an overview of these techniques. So why we need characterization of a material? Suppose you have a substrate, you want to deposit a sensing material, and you want the sensing material to be in very pure form, otherwise it will not give the desired sensor characteristics, sensing behavior. After depositing the sensing material, you will go for characterization and you will see whether your material is pure or not, what are the different properties of the material, and based on that we can see you can say whether this material will work as work in your sensor or not. So characterization is very important. It is also one a very integral part in fabrication techniques. So here the first technique that is mentioned here is Raman spectroscopy. not sure whether you have heard about Raman scattering and Rayleigh scattering or not. So what happens? Suppose this is some material and light is incident here. There are few phenomena can be happen. The light may be absorbed by the material, the light may be transmitted through the material, or it can be reflected back. Another phenomena that can happen is scattering. So light will scatter like this. Now there are two types of scattering. In case of Raman scattering, what happened? Say your incident light have a certain wavelength lambda, and the scattered light will have a different wavelength, some lambda bands. This kind of scattering is known as Raman scattering, and if it is the scattered light have same wavelength or same energy, then it is known as Rayleigh scattering, and if it has different wavelength, then it is Raman scattering. Now say Raman scattering is observed in different molecules. So you have a molecule here, this is the bond, and you have this molecule in your material, in your science material, the film, or the material that you are going to characterize. Now say you incident a certain wavelength of light here, and it will show Raman scattering. Now depending on this molecule and the molecules, the way it vibrates inside the material, that will give this is suppose lambda and this is lambda dash, and this delta lambda, which is the difference between this two. This delta lambda will depend on this molecule. Okay, so that is why Raman spectroscopy is used to characterize a material that gives information about molecular vibration. I will not go details into that, but it gives molecular vibration and information about the chemical composition of the material. And now it can give many other information about your material also. I am also not very aware how to analyze the Raman spectroscopy result. This is the job of a material scientist or the people who work in material science. But to get an idea about your material, you can do Raman spectroscopy and see whether you are getting the desired material composition or not. Okay, based on the delta lambda, which is known as the Raman shift in case of Raman spectroscopy, and whether you are getting the desired Raman shift or not for your material. So how you compare, how you do the analysis for certain material, the Raman shift is already known, so you will do the characterization, you will compare your result with the already known result, the standard results, and if it is giving similar result, then you are sure that you have this kind of chemical composition or the material composition in your deposition or in your film. Okay, so this is about Raman spectroscopy. Next is XRD. So it is XRD, it is X-ray diffraction. So it uses the diffraction of light, and the source used here is X-ray. Okay, so X-ray diffraction is based on scattering of X-ray with the crystalline planes of a material. So what happens, suppose inside your material, these are the atoms. The atoms are arranged in a certain patterns, so that is the crystallinity of this material. And you can imagine different planes here, like this is one plane, this is one plane. Okay, now x-rays will be incident here like this. So this is in straight line. Line is not very proper. It will be scattered like this. Light will x-rays will also incident here, be scattered like this. Now the light in this path and this path, there will be a certain path difference. Say this is the distance between these two planes, which is denoted by d. So and say this is theta, incident angle. So this will be d sine theta. Okay. Now as per the Bragg's law, or as per the Bragg's law, how constructive interference will happen. Constructive interference means these two rays will interact constructively. That means will add up. It will not cancel each other only when this 2d sine theta is equal to n lambda. N is an integer. This is known as ordered diffraction, but for the time being, let's not worry about this. The point you should remember is that if this distance is which is d sine theta, and twice of that, if it is equal to the lambda, that is the wavelength of X-ray, then only we will get constructive interference. That means if this x is your theta, and if it is your there will be a detector here, okay, that will detect the signal of these scattered light. Because of constructive interference at certain theta, that will give a peak. So this is intensity, right? This will give at certain theta. Now this theta, the peak you will get, that will depend on the theta and d. Of course it will depend on lambda, but lambda is fixed for this X-ray diffraction machine, and the peak you will get basically depending on d. So you will know the distance between these two planes, these two crystallographic plane, that will be different for different material. Say for material A, this distance will be different, and for material B, it will be different. Now based on XRD result, we will get the information about the crystalline planes of the material, and based on that we can actually identify the material. Okay. So that is about XRD. The next technique is UV visible spectroscopy. How a typical result of UV spectroscopy looks like. In the x-axis we will have again intensity. It can be transmission or it can be reflection. And in this axis we will have wavelength or frequency. If it is in wavelength, it will be in nanometer. It will start say some 200 nanometer wavelength to visible spectroscopy will be 800. Generally it is higher than that, but it will give the wavelength. We will have the wavelength range that corresponds to UV and visible spectrum in electromagnetic UV and visible range in the electromagnetic spectrum. Now suppose you have a semiconducting material, so you know that it will absorb light if the band gap is if the incident light energy is greater than or equal to the band gap of the semiconducting material, then it will absorb. What will happen if E is less than EC? This is your EC and EP. This is your semiconducting material. This is your band gap. If the incident photon or the incident light energy, which is E, and E is equal to h nu or hc by lambda, if this energy L is less, it will transmit through this semiconducting material. It will not absorb. Okay, so this is lambda, right? If you already know the concept of critical wavelength, right? If the wavelength is, so the energy should be greater than or equal to EZ, so this is hc by lambda greater than or equal to EZ. So your wavelength should be at some critical wavelength, hc by lambda c is equal to EZ, that is known as the critical wavelength. And for absorption, E should be greater than EZ, that means lambda should be less than lambda c. So if your y-axis is absorption, then you will get a pattern like this. Okay, this will corresponds to lambda c, say. Or if your x-axis is transmission T, then it will be like opposite, right? If this is lambda, if this x-axis is frequency nu, let me write hertz, this is transmission, then it will be opposite, because frequency should be higher for absorption. So your absorption curve will be also opposite if your x-axis is frequency. Okay, now based on this critical wavelength, you can get the information about the band gap of the material. This may not be that straightforward, but there are techniques to extract the band gap of semiconductor using UV-based spectroscopy. In case of metal, we get information about plasma frequency and all of that. I'm not going into details of this, but this is one material characterization techniques, and the basic of UV-based spectroscopy is this. The last technique that was in the option is SEM. So what is SEM? Scanning electron microscopy. Now here again, like I have given you the comparison of photolithography and e-beam lithography. What we do in case of optical microscope, the one that you must have seen, so it uses visible light to see, right? Some patterns we cannot see by naked eye. We put it in a microscope and we see using a optical microscope. Using an optical microscope, we can see patterns which are typically, like we can very easily see patterns in micrometer. It will be actually difficult to see like in nanometer size patterns if the dimensions are very small, like 10-20 nanometer we will not be able to see using an optical microscope. The reason is again same. It depends on the wavelength of the source, and there is other concept of diffraction limit, but the point is to remember is that the optical light source uses visible light, that the wavelength range is 400 to 700 nanometer, and we cannot see very small features using optical microscope. So what we do, we use electron microscope. We use the wavelength of electron, which is much smaller compared to visible wavelength, and we use electron wavelength to see smaller features. We talk about nano devices like nano wires and different nano patterns. If we don't actually visualize, if you cannot see the patterns, how we will say that those are nano rods or nano wires, right? So see those patterns, we use SEM, electron microscope. So this is one type of electron microscope. Again, lambda for electrons. Lambda is equal to h by mv. You can do a rough calculation. The velocity of electrons inside a material that you can get from internet. H you already know, Planck's constant, and m is the mass of electron. So you can get roughly what is the wavelength of electron, that will be in nanometers. So you can do a rough calculation. You will know that it is much smaller compared to the visible wavelength. Okay. So SEM can provide higher resolution compared to optical microscope. So that's about brief description of different characterization techniques. I hope these techniques are clear. If you have any question related to this, you can ask. These topics are electron microscope itself is a big topic. Visible spectroscopy is a big topic. So I have just tried to give you an overview of these characterization techniques and why we need these techniques in case of sensor fabrication. So is there any doubt? I don't have much time, so I will not go to the next questions. Maybe we can discuss in the doubt clearing session or the extra session that I am going to take. No questions? Okay. So, are you guys all from EC background, or there is someone from different background? Because many things yes, we try to upload it as early as possible. I don't know about other TAs. I think he also uploads. You can check in the announcement section in SWAYAM portal. It will take some time to upload it takes certain amount of time to upload and do the processing in YouTube, but we try to upload as early as possible. Okay. So many things I say, considering that all of you are from EC background, like you know about electronics and basics of semiconductor and other things. If you find any difficulty and if I should go slow, then let me know. I will do it accordingly. So if there is no question, then thank you everyone. I hope the session was useful, and let's meet in the next session. You okay. See, many things may not be in the PPT, so it is always better to go through the videos. Sometimes the faculty explain many things, we will not write it everything in the PPT, so it's up to you. My suggestion will be that you go through the videos at least once before the exam if you have applied registered for examination. Okay. Thank you everyone. Thank you for joining the session. Let's meet in the next week.